Okay, welcome to class. This is the video key to these Lewis structures, which I posted. Okay, A, B, and C, this is the general format of what we are going to do. These are the easy ones, so I just put them there. Okay, well, NCl2. So, draw an N, Cl, Cl, Cl. You know that these are all going to be bonded to each other, like that. And then you just count however more electrons there are. Nitrogen has 5, 1, 2, and then 3 of the bonds, that's 5. Chlorine have 7, so 6 lone pairs surrounding each of them, and I'll draw them while we're starting out. And, well, that's it. And then I look to see if there's any Lewis structures that are possible. I think there are not. Okay, these are polar bonds. There's a dipole going that way, that way, that way. So it is polar. There are 4 electron domains. So it is the base shape is tetrahedral. The shape of the molecule is trigonal by a trigonal pyramidal. It's polar. And sp3 is the hybridization on N. Okay, COCl2. Carbon's probably the central atom. So I know that at least everything is bonded to each other. And then I'll just draw the electrons. Oxygen has 6 electrons. So that means that the oxygen CO bond, those are all carbons. And then carbon has 2 more in the Cl bonds. And that works out nicely. Okay, so those are all the electrons. You probably want to count the number of electrons, that are fine, but that does not follow the octet rule. So these electrons are there. And that's a double bond. Okay, that's cool. So the polarity on this one, there's a dipole going that way, dipole going that way, dipole going that way. So that's actually kind of tough to tell. I don't know. The base shape is trig planar. The molecular shape is trig planar. It is polar and sp2 hybridized. That is for sure. Okay, we're moving on. IO2 minus. Okay, so let's count the electrons on this one for sure. Oxygen has 6, iodine has 7, oxygen has 6, so in total that is 8 plus 12, which I call 20 electrons. So let's put all of them by themselves. Okay, so iodine has the 7 electrons, 2 in the bonds, 2 in the lone pairs, 2 in the bonds, 1 in the other lone pair. And oxygen has its 6, and it has an additional one because it's a negative charge. So it's there. And then I look at that briefly, and I wonder if that is the correct Lewis structure. I mean, the octet rule is satisfied. I look at the formal charges. Oxygen wants 6, it has 7, so it's -1. Iodine wants 7, it has 4 plus 6, which is what I call 1. Oxygen wants 6, it has 7, formal charge is -1. I think that these electrons go right there, and they're shared, which would make iodine have 7. It's an expanded octet, but iodine can't do that because, that's iodine. And that works. However, this does not imply that the negative charge on the left oxygen is also simultaneously on the right oxygen. So that means I want to draw a Lewis structure, and you can put brackets around it. Or let's do horizontal Lewis structures. So the structures on the left and the right are not different. You just need to draw both of them to imply that the double bond is on the left and the right, and the negative charge is on the left and the right at the same time. Because electrons are kind of cool like that. Okay. I'm actually going to check the internet to see if that's the correct Lewis structure for IO2. How about that? It totally is. How about that? Okay, so it is the base shape. This is a good one. It's 1, 2, 3, 4 electron domains. So it's tetrahedral. The molecular shape, however, is bent. It looks like water. And the hybridization on the central atom is, of course, sp3. And the polarity, because it looks like this, is it has a net dipole. It is polar. Okay, that's cool. Okay, Cn minus, you should look at this and know that it is cyanide. If you don't, that's tricky. So Cn, let's just draw them having all their electrons. Wow, it's almost like I know what's going to happen. And then there's another electron here because it's a negative charge. So there's 4 from carbon, 5 from nitrogen, 1 from the negative one. So that is 10 electrons. So let's put the other one right there. And, well, let's just connect these and just see if that works. And it totally does. And, we're done. There's just 2 atoms, so who knows what the central atom is, but let's say it's a linear sp. This is most definitely polar. Nitrogen is more electronegative. Okay. Silicon tetrafluoride. This is a tricky one. I do not know what's going to happen. Okay, so let's draw let's all draw fluorides with their electrons. They have 7 electrons. The 6 of them are in their lone pairs, wherever they are. I don't think I'm going to draw them. Silicon is right under carbon in the periodic table, right? Is that right? Excuse me. It is. Okay, sorry. And there's 4 electrons there. So let's just, maybe it's the most simple answer. Oh, I guess that's actually not too complicated. How about that? So it's tetrahedral, base shape, tetrahedral molecule. Is it polar? It is nonpolar because it certainly has polar bonds, but they all cancel each other out. And the hybridization is sp3 because there's spp, 4 things attached to the central atom. Okay, OCl2. Okay, it's let's draw everybody having their oxygen has 6, chlorine has 7, one there, and then, okay, I'll draw it. The 6 lone pairs right there. Okay, let's just kind of conjoin these. And, well, that's it, right? I guess that's it. Base shape is tetrahedral. The molecular shape is like water. It's bent. I wrote water. Okay. It is, of course, this Lewis structure doesn't show the shape of it. This is the shape of it, which, of course, you can see has a dipole going that way or the other way. I don't know which is more polar, oxygen or chlorine. They're actually pretty close, so it's not super polar, but there's a dipole moment, so I guess it's polar. The hybridization on the central atom is sp3. Okay, ICl4 minus, ICl, Cl, Cl, Cl. Okay, like we know with the halogens, there's 1 electron, and then they each have their 6 electrons that they hold on to. Whenever you have fluorine or chlorine or bromine, it kind of looks like this. And we have another iodine there. So that has 1, 2, 3, 4, and then another 4, which we're going to draw right there and right there. So iodine has 8 electrons because there is 7 plus 7 plus 7 plus 7 plus 7 plus 1, which I reckon to be 36 electrons. I would definitely count the electrons in this type of problem, and I have that many. So let's say that's a bond, that's a bond, and then that's a bond, that's a bond. Okay, can you see that? So it has, the essential iodine has 4 bonds and 2 sets of lone pairs. And all the other chlorines are, they have what they have. Okay, so the base shape is, there are 6 electron domains, so it is octahedral. The shape is square planar or seesaw, or I think that's what it's called. Because if we look at this drawn it look like that, which is square planar. Or if one of those lone pairs and the other thing was switched, then it would be seesaw. Cool. Okay, it is polar when it's seesaw, non-polar when it is square planar. Okay, and what the centralization, the hybridization on the central atom is sp3d2. How about that? Pretty cool. Okay, H. Phosphorus, fluoride, fluoride, fluoride. Okay, let's draw the things on the fluorides. Okay, phosphorus has 5 electrons. Let's draw 1, 2, 3, 4, 5. And then let's just kind of connect the dots and see if the octet rule holds. Okay. Wow, the octet rule actually does hold. There's no expanded octet. I think everybody's happy like that. I'm happy like that. So the base shape is tetrahedral because there are 3 electron domains on the central atom. The shape is like ammonia, which is trig, pyramidal, trigonal pyramidal. That's right, I think. Is it polar? Let's draw what it looks like spatially, which you can clearly see that is polar because fluorine is there at an angle, so it is polar, and the hybridization is sp3. Huh. These kind of repeat each other. How about that? Who'd have guessed? Let's see. We have about half. Ooh. Okay, onward. Okay, now it's we're at NFO. So, what's the central atom? I don't know. Let's just say that nitrogen is, and then we'll draw a Lewis structure for it. And if we can't get anything that makes any sense, I guess nitrogen isn't the central atom. So that's how you figure out what the central atom is. So nitrogen has 5. Let's talk about fluorine has its 7. Oxygen has its 6. Nitrogen has its 5. Let's put 1, 2, 3, 4, 5. Okay, and I used my eye of faith to look into what I thought the Lewis structure would be from the get-go. But those are all the electrons, and then you just kind of play a game where you attach them together. And then I asked myself, is that a reasonable Lewis structure? All the things follow the octet rule. There's no formal charges on any of these things. This is... Oh. I forgot to do what I told you guys to do in the problem. Iodine here has, let's see, it wants 7, and it has 1, 2, 3, 4, 5, 6, 7, 8. So it has 1 more than it needs, so it has a -1 formal charge. That's my bad. Sorry. Okay. So, what's the shape what's the base shape? There's 3 electron domains on the nitrogen. It is trig planar. But the molecular shape is bent, but not like water is bent. It's a different kind of bent. And then we look at the polarity, which looks like this. And there's a dipole going that way, a dipole going that way, because fluorine and oxygen are both more electronegative than nitrogen. So there definitely is, definitely is polar. And it is sp2 hybridized. Nitrate. So when I say nitrate, you need to know that nitrate is... That's basic. Okay, so there's a nitrogen, an oxygen, an oxygen, and an oxygen. And let's play a game. Nitrogen has 3 electrons, 5 electrons. 1, 2, 3, 4, 5. And oxygen has, ooh, this is going to be tricky. 6 electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm going to redraw the nitrogen's electrons. Okay. Oh, and then there's another electron. See, this is what happens when you don't indicate the total number of electrons. There's 6 from oxygen, 6 from oxygen, 6 from oxygen. That's 18 plus 5, would be 23, but it's really 24 because there's another electron. So there it is. And I think that these lone pairs kind of extend to form a bond. And so that's a structure with the right amount of electrons, but we see that nitrogen does not follow the octet rule. So what happens is that these electrons, maybe these electrons, or, okay, these electrons come down and they form a bond, nitrogen, and then there's that. However, that's correct, but this is not complete because I need to find a way to indicate that that's not correct. That can't be correct. Is that right? What's the formal charge on all of these? See, this is what you do when you want to know if something is correct. The formal charge of this oxygen is 0. This nitrogen wants 5. It has 4, so it's +1, -1, -1. So that's, the charge adds up to 0, but I don't think there's a -1 next to a +1. I think that another pair of electrons comes down and they form another double bond. And I guess I'm inferring this because of what I know about formal charges. And now there is just a -1 charge on that oxygen, and everything else is 0. So I think that's the better drawing of, I take that back. That can't be right, because nitrogen can't have an expanded octet. Does it though? It has, yeah, it totally does. 1 second. My bad. Oh, so I guess it was what we talked about, what I drew earlier. This right there. And it has to be that. That's the only option because nitrogen cannot have an expanded octet. That's super cool. But this is still not complete because I need to find a way to imply that the negative charges in oxygen exist on all of the oxygens equally, which means I need to draw the resonance structures. And yes, I do need to draw this, even though it seems like a waste of time. But this is the way to indicate, like I said, that the negative charges is not centralized on just 2 of the oxygens. It's on all of them equally. You could say that it is delocalized, which is what it happened, which is what it is. And that's true. That's what it is. Okay. So the base shape is trig planar. The molecular shape is trig planar. It's not polar, even though there are 3 dipoles, because it's all on the plane. It all cancels out. The hybridization of the central atom is sp2. Sulfite. Okay, another thing you should be able to tell. Let's see if this one works better. Sulfite, SOOO. How about that? So this is oxygen is 6. Sulfur has 6, but what's the charge of sulfur? I mean sulfite. It's 2 minus, right? So it has, let's put 8 on that sulfur. And let's put 2 there. 2 there. 2 there. And 2 there. So you connect the dots. Turn this lone pair, this pair of electrons into a single bond. Connect those dots. And that looks like sulfite, maybe? 1 second. These are good questions. Do I have the right amount of electrons? Yeah. So what is this is good. Let's talk. What's the formal charge? It's oxygen on the bottom left wants 6. It has 7, has -1. A negative charge on oxygen is pretty standard stuff, pretty standard material. Oxygen, this has 0. Sulfur wants 6. It has 1, 2, 3, 4, 5, 6, 7. It has -1. Okay, but I ask you this. Will a -1 charge be on sulfur or will it be on oxygen? It will be on oxygen. Oxygen likes negative charge better. Okay, so let's do some fancy work. And let's put this shared pair back on oxygen. Now that has a -1 charge. Sulfur has wants 6. It has 1, 2, 3, 4, 5, 6. And that looks to me like a good Lewis structure. Yeah, that's it. But this is not correct totally, because this does not correctly indicate that negative charge on those 2 oxygens exists equally throughout all the oxygens. That's another word for resonance. So yes, you have to draw. That's a resonance arrow. And like I said, if you don't want to draw the lone pairs, at least draw all the charges. In fact, always draw the charge on an atom in the Lewis structure. That's it. Okay. So this is it's a tetrahedral. There are 4 domains. It is 4 domains. One of them is lone pair. It is trig planar. And is it polar? Well, let's look at what it looks like here. And we can see that they're all the pole is going down, so definitely is polar. And the hybridization on the central atom is just sp3, because it is that. Okay, HPO4, 2 minus. That is tricky. But if you recognize that PO4, 3 minus, is phosphate, which you know because you memorized it, it'll be easier to figure out where that hydrogen goes. So let's just draw phosphate really quick. Oh, 4 oxygens, that's crazy. So they have their phosphorus has 5. I drew it with 8. Oh, nope. I drew it with 8 because this has a 3 minus charge. And I just think this is going to bring me good luck. I drew the 6 on oxygen. So this is, right off the bat, this follows the octet rule. But let's make some commentary on the formal charges to see what we're talking about. Oxygen wants 6, it has 7. And that's the same for all of these. Okay. Phosphorus wants 5, it has 4, so the total charges is +1. That the charge does add up. I'm going to confirm with the World Wide Web if they think that I drew the right one, because I feel like there should be a double bond. And I'm correct, yeah, because once again, what are the odds that a negative charge is going to be right next to a positive charge? I think it's more likely that they cancel each other out. So these electrons, they go down here. And that's a more reasonable thing because there's not a negative and a positive charge. I mean, obviously there's going to be 3 negative charges because that's just because there's the 3 negative charge. But we forgot to add hydrogen, so let's add hydrogen right now to that boy right there. The electrons all add up, if you don't believe me, right there. So that's hydrogen. So now that is 2 minus. I guess we did 2 at the same time. So, but this is not correct. This does not yet imply that these negative charges on the oxygens are shared between the other oxygens. Not the oxygen that has the hydrogen on it, but you know. And yes, maybe this seems like a waste of your time, but you do have to draw it. This is the only correct answer. Because the negative charge exists on all of them. So let's comment on the bond order, like sulfite, for example. The bond order between the S and O is 1 and 1/3, which I like to call 4/3. The bond order is on nitrate is 1 and 1/3. Oh well, that's not that exciting actually. It's the same thing. Maybe you're asking how I figured that out, because there's 1 single bond, 1 double bond, another single bond, double bond. Well, this is not. I'll explain that maybe later, but hopefully you can see it. Okay, I'm going to cut this video in half after I write the base shape is tetrahedral. The shape of the molecule is tetrahedral. Is it polar? It is not. Well, let's just leave it at that, non-polar. And the hybridization is sp3. Okay, stop.